So in this video, we'll start seeing another broad family of methods that are coming under the headline of planning. In this time, as compared to an earlier video we have seen, planning actually will happen with interactions with the environment. So the environment will actually be able to send us a signal, a reward that it will, in broad terms, being used to guide the strategy of actions that we will take in that to act optimally in that environment. And that environment will also be stochastic, which means that despite the fact that we may be intending to reach a desired state when we perform a specific action, the stochasticity of the environment will actually lead us to other states other than the intended state. Planning with interactions also take a form of two methods as well. One is called Markov decision processes, and on those we'll be assuming that we have an understanding of the model, complete model of that environment, the model dynamics as we define them. And the second category will be reinforcement learning, where in this case we will need to learn those dynamics in order to perform optimally in that environment. So let's now introduce some important notation in our attempt to start the discussion about introducing, if you like, the MDP or the Markov decision process problem statement. So we will be having, if you like, a diagram like the one we had seen in earlier kind of videos where the agent is sitting on one side and the environment on the other. And what we actually, as a reminder, what we mean by environment, we mean everything which is outside the scope, the control scope of an agent. And this means, for example, in a self-driving car, let's say a robot, I've seen it in another video, that everything, let's say, outside of that control responsibility of that kind of vehicle, including other vehicles, the pedestrians and so on, will be considered to be the environment. And so the agent is going to be taking some kind of an actions, and the result of those actions are going to change the state of the environment. The state is always something which is going to be assumed to be fully observed and contained within that kind of environment box. And so the agent being, let's say, in state ST, as it is shown in the diagram, is taking some action AT, and then the results of this action are a change state ST plus 1 and a reward signal RT plus 1, which are sent to the agent to be able to so as we have discussed in another video, let's try to put some kind of notation about this kind of agent environment interface. We have seen agent environment interfaces before in another video, but now the emphasis here will be on introducing specific notations to introduce the Markov decision process model. So in this setting, we have an agent and we have an environment, and the agent being in state ST decides to take an action AT, and that action changes the state of the environment, and it leads the agent to a next state, which is ST plus 1 here, and the environment is sending that reward RT plus 1 for the agent to be able to consume it, and we'll see now exactly how this consumption will, what it will result to. So the important points here in this kind of setting, let me just go back to that sort of writing a little bit about this kind of notation. So we have, if you like, the following which is actually happening. So we are in some kind of a state ST, which capital ST will be the random variable that indicates the state at time t, and let me call this to be S. We're taking some kind of an action AT, which is going to be A in this case, and we are led into a reward ST plus 1. We are getting a reward for that and a new state S prime. So this is definitely an agent decision, and this is the environment responsibility. So that's the responsibility of an agent, that's environment responsibility. Now that we have reached this kind of state S prime, we will be taking an action. We'll be taking an action. This action is, again, the arrow at plus 1 is equal to, let's say, a prime. Prime in our kind of notation over here means next. So next state here, next action, moving over, and then this is agent, moving over to RT plus 2 is equal to R, and then ST plus 1. Okay, so that's basically it. R is a scalar, so R is a scalar, and is actually called reward. So in terms of notations, we have A for action, and S, small letter S will be the specific state, and the prime operator will be, stands for next. So instead of having, if you like, this kind of complicated notation over here, we will probably be omitting in some instances the capital A, which is basically the name of the variable, and we can just quote only the specific instance of that variable, which is the specific action. So this, of course, continues, sometimes continuously forever, or sometimes it's also going to terminate in what we will be calling an episode. Okay, so in terms of notation, again, we have divided this whole experience into multiple interactions, so that we'll call SA R, comma, S prime, A prime, R prime, comma, dot, 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 and so on. So these are basically our interactions, and this is basically our experience. Okay, so the MDP problem, and let me also go back to the site to introduce now the notation that we have just quoted. All right, so we see here the state calligraphic S is the set of states that we have. The same with calligraphic A as the set of finite actions that we have. So we have a finite MDP problem. We have a finite set of actions. All of this notation that I just mentioned. T is a time index, but is basically here is not necessarily has to take the semantics of time. It is basically some kind of sequential index. And capital T is a time where our episode kind of terminates. And let's say, for example, in the game, let's say of tic-tac-toe, the game ends with one of the players kind of winning, and T is going to be the maximum possible duration of a tic-tac-toe game ever. And then the termination may actually happen before that capital T is reached. So the episode is the horizon from T is equal to 0, where the interaction starts, to T minus 1. And tau is going to be called a trajectory. It is this kind of sequence of experiences over that kind of over an episode that we have just defined. So these triplets of states, actions, and rewards. All right, so these are basically the sort of starting notation for defining the MDP problem, and then we'll see the last two how they get to be defined. And then now let's go back to that sort of whiteboard over here, and let's define now formally the MDP. So the MDP, I'll call it as calligraphic M, is a 5-tuple. So it starts with a set of states. It is capital P, calligraphic P, will designate here the so-called transition. Model. Okay, so this is the set of states. The transition model, the reward set of reward functions that we have defined, and set of actions, set of reward, set of actions, and another factor that is called gamma, which actually stands for the discount factor. Okay, so this is the discount factor. We'll see how the discount factor gets to be used. I should also point out that in many textbooks you've seen a slightly different notation. However, the number of textbooks is kind of equally divided. So here we have adopted the SATO notation, which is really the standard reinforcement learning textbook out there. So especially with respect to the reward, you may actually see the reward not with T+1, but with T in some other textbooks. I just want to mention that just in case you are comparing notes and you are looking at other sort of sources to understand Markov decision process rather than the notes. Okay, so I think it's worthwhile kind of drawing a diagram. And in this kind of diagram, what we will draw here is basically some kind of a dependency diagram, a dependency kind of network. So we have here the state, first one, we have this state S that transitions via the transition model to S prime. And this transition is effectively sort of due to two things. First of all, the action A induces the transition. So S prime has dependency on this action A. And also the reward that we are getting also has dependency on both action and the state that you are in. So this diagram, similar to the other diagrams we've seen in some other videos when for example, we're doing hidden Markov models we've seen in the probabilistic reasoning over time. They do allow us to kind of come up with interesting probabilistic models that govern, if you like, the operation of a Markov decision process. And here it is actually evident that R and S prime are determined from S and A. Okay, and let's keep that. So let me write this down. R, reward, and S prime take place, or not take place, but are determined from at the same time. When we execute the step function with arguments S and A. Okay, so this kind of step function is the one that kind of transitions the environment and also send us that kind of reward. And this is basically the two arguments it returns, two things that returns this step function, two things that are coming as input, two things that are being returned. And based on that, we can definitely start writing the first, if you like, probabilistic model that will definitely will be part of what will be called MDP dynamics. So first we are expecting to see probability distributions, and the shape and form of these probability distributions will be definitely governed by this diagram, which is a dependency diagram that sort of showcases dependencies between the instances of underlying random variables here. And so let's see one obvious one. So the first one I want to cover is the probability of S. Prime given S, comma A. S prime given S, comma A. So what is the probability of the next state, given that I'm in state S right now and I'm committing to take the action A. So this is effectively what will be governing the so-called transition model. We'll be calling a transition model. And I think in terms of notation, we can sort of, not in terms of notation, but we can actually write this transition model as some kind of marginalization over a very interesting, that this is what we'll be calling MDP dynamics distribution for all the rewards that belong to the set of rewards R. So we have the marginalization over all R of S prime, comma R given S, comma A. Okay, so this is what we will be at the end of the day calling MDP dynamics. This will be the complete set of all of the whole behavior of this kind of diagram, and we are obtaining, if you like, the transition model by marginalizing over all rewards. Now, this is what we call the sum rule in one of the videos when we're reviewing probability, the laws of probability, the two laws, the sum and the product rule of probability. And that's basically, it's a kind of a straightforward summing over R to obtain the transition model. Okay, so this transition model will actually have an example in a moment. So that's the first type of MDP dynamics I want to explicitly call out. And the second is this probability distribution, which is the probability distribution over rewards R, given that we are in state S and A. So it is this guy over here. So this can also be written as a marginalization now over the S prime set of from the set of all states that we have in the problem over all of the next states that belong to the calligraphic S, or the set of all states that we have in the problem. And this is basically P of S prime, comma R given S, comma A. And this is the probability distribution of rewards. This transition model is the probability distribution over next states. So these two, as you actually can see, they are directly related to this quantity, this identical quantity that we'll be calling from now on the so-called MDP dynamics, which is a probability distribution, a conditional probability distribution of the next state and reward, which, as we said, are determined jointly in one step. And given the fact that we are in state S and took an action A.